Hello, everybody, and welcome to our class where we're going to start to analyze our chip data. We're going to use R code and we're going to start looking at what are these peak files, what is the information in them, what's the important information to us as we're going to start to analyze them. So I think it's really important to understand the fundamentals of the type of data you're working with and how to maneuver around that. So let's get started with that. And so I'm in the class GitHub here in classes. We're in our basics. We just learned R Studio, so we're going to move right back over there. I'm going to stop starting from the GitHub, I think. And today we're going to be running our basics RMD. You can navigate to that in your R Studio now. That's here. So for our class here, I'm the JR folder. And in there, this is where you would have cloned the class in class 2023. And then classes 04 are basics, and then our basics, where we're going to start running some R code today. And that is what I have loaded up here. We talked about sort of the title page here and some of our setup factors. So let's run that and get set up. And to run things, you just do Control Enter here and load these libraries. I already have them loaded, so you might see some stuff going. You can also use this green arrow button here, but I don't like doing that. I like kind of going line by line. So here's just a path to where to go if you're in class to your folder where I just sort of navigated. Again, you want to always set your working directory to where you are. And so right now we're in our basics, and I'm going to set that as my working directory. So any results we have that come out from working in here will go either directly in here or into our results folder. We'll head to them. Okay, so we don't start overwriting each other's work. We're going to set our first variable. So this is the object here. The name will be called base path. And in R, this arrow here means assign this object name this information. In this case, it's just a string of text, and you'll want to change it to the name of your folder, or if you're working directly in here, just leave that as the end and delete this. And if you run that with the Control Enter, you will get an environmental variable that has your base path with where your class 2023 folder is. So it should be to the folder just before your class 2023. Okay, and so in there, what we can do is to read in a file. So let's say we want to read in our first pull2 peak file here. Pull2 peak 1 is what we'll call it. We'll use the assignment operator here to assign that and use this read TSV function in R, which is reading a tab separated file, is what our peak file is formatted as. Then this is a base R function here that says file path is, and all functions in R are sort of with a parenthesis. So read TSV, if you just tab forwarded it, it's going to leave these two parentheses, and inside the parentheses means, okay, this is the function. What are the parameters to enter into that function? So we have read TSV opening up to do the function file.path, which will paste the base path here to your folder, and then the rest of the file path to the data in your Nextflow pipeline. So I called mine 03. And if we go back to classes where we ran the data was in 03 Nextflow, and I have my 00 pull2 NF core run here. One handy thing is you can run to there. We're going to go into that results folder, but you can use copy folder path to clipboard, and that'll tell you the path to there, and you can paste it in here. So now, instead of just rest of file path, which is useless, we're going to actually do this to read in where my peak files are. And to refresh you, it's in results, BWA, merge library, max, broad peak, and then we're looking for any file that's called peaks.broadpeak, and we'll get into that as well. But for now, we're just going to tell it exactly which file we want. Pull R2 underscore R1, that's here, and then the .broadpeak file is here. Okay, so nice thing about setting your working directory is now I can just go back to it by clicking go to working directory right back here. Okay, so let's read in our first peek file and see what we get. So we're just using a read function, telling it where the file is, and it's going to read it in. Okay, so we have an object in our environment. And so the environment is a place we are going to go a lot here, where we're just going to click pull our two there and see what that object is. You can look at it this way by the drop down blue arrow here. It's a bit harder to read this way at first, but I bet in the next few classes, you're going to be looking in there all the time. So I just double clicked on it and I get the table that has the chromosome, the start, the stop of the peak, the name of the peak, and some other features we'll discuss in just a minute. But what you can see right away is our row names are here in the black. This is just like an Excel sheet, so to speak. And on top, though, the header has our data in it, and that is not good. This is just an example of why you want to be careful and always check what you just created and what your data is looking like. So we don't want this to be our column header because we're not going to include that peak in our analysis, and things will be off by one number and it'll just cause a whole mess. So read TSV has another aspect we can add in there. And so when you're in a function, you can tell it the first parameter here is the file path for read TSV. And then the next parameter can be separated by a comma and then say call names equals false. And you'll start to get used to these and copying and pasting them as we go. So be patient with yourself. It's a lot to start to remember. But the comma is really the key here, that we're saying read this file in this path. And once you do that, don't give me column names. Make that go false. So let's rename it the same name we just read in, poll to peak 1. We can see there's 33,581 rows. That's the observations, and 9 variables. Those are the columns. So in R, everything is always rows and then columns. And we'll see that quite a bit. Okay, so now if we run that, and it's just going to rename it. So you want to always be careful when you name something the same thing, because now we're going to write over that. But in this case, that's what we wanted to do. So we can see it made generic names for the column names X1, X2, X3. That's not very useful. And I'll tell you what these columns are in just a second. But it's good we don't have a header now. So all of our data is in here. So we're one step closer. That's good. And so what that file is a .broadpeak. You can just Google .broadpeak column names, and it'll tell you that. I have it also listed here, that you always start with the chromosome, the start and the stop of the peak, the name of the peak, score, strand, signal value, p-value, and q-value. And if you have less peaks, they're in this order, or less columns, they're usually in this order. You can kind of tell by what information is in each column. So if we wanted to rename the first column in poll to peak 1 that we just have, that right now has this unfortunate X1 that doesn't tell us much. Let's say we want to name that chromosome. So we can use as the names function, again, in parentheses, poll to peak 1. So it's saying the names of this object should be called, and then this is the text chromosome. So let's see what we get here. Okay, so it doesn't like that because there's 9 columns. Okay, so we have to now start to index. This is the console here where the errors come out, and it's saying, hey, look, I can't do this with 9 columns, just add one thing to it. So now what we'll do then is we'll index into a specific spot. And so we could do the same thing here and say we want to go into this object, poll to peak, and we want the first column to be chromosome. That should work. And if we look here, we can see now our first column is named chromosome. And so we could go through manually and name the second one with start. Here again, Control Enter to run it. And now we'll see that we have chromosome start, but this would get kind of tedious to keep doing that over and over again. So what we can do with this names function is say names of poll to peaks equals, and we'll see this C a lot and paste a lot. And it's basically saying just make a string of these characters. And so these are the column names that we want on there, and they're characters, so they're in these quotes, and the C will put them all together, and then put it in the name of each column. So it's kind of doing it's going to say, okay, I have 9 values and 9 columns. I'm going to just put them in this order. And so if we, and then the C is just making it a string, and we'll see this more and more, and it'll start to make sense. But it's saying, take the names, take this string, take each entry, then put it into as the column name. So if we do that, and now take a look at our object, awesome. We are good to go and have all of our information here. On strand, it's always going to be a star or a dot, which means, because ChIPseq, that you don't tell which strand the peak is on in the DNA, it's both strands. So we don't have to worry about that. We will with RNA-seq and some other types of data. Okay, that's great. We have that. And now we're going to index some more. So we saw here, we can index into a column number by the square bracket outside the object. And so if we have the square bracket inside the object, what it's going to do is go in and only take out that information from that table. So you can imagine going into Excel and just grabbing a subset of information that you're providing it. And what we see here is kind of weird is, what is this GLO thing? Well, it's a chromosome that has not been placed yet, and it's called a contig. We don't want those. They kind of mess up the data. We only want to deal with the regular chromosomes 1 through 22, chromosomes M and X and Y. M is for mitochondrial. Okay, so we can go into our POL2 peaks file, which now has this GL whatever in it, and only get out things that are in the POL2 peak object in the chromosome column. So that's where this GLO thing is. And then we're going to use this handy tidyverse function. This is our first example of why tidyverse is so great, is we can say, tell me take this chromosome column. So we index with a cash sign into the first column in chromosome, and it'll autocomplete it'll know the column names and then autocomplete to that. And we say, okay, take this object, subset it, because we're going to have the square brackets right next to it instead of outside the parentheses like we did before. So we're going into it, and we're going into the chromosome column, and we're saying, give me only the things that are in that match these names. And this is that C to make a string of vectors. And we can then use paste 0 to make a list of chromosome 1 through 22 inside the paste 0. So the paste 0 is going to take chromosome and make chromosome 1, 2, 3, 4. It's almost like a little mini for loop here, that this is going to make 22 chromosome 1, 2 through 22. And this outer thing is going to paste all of those in between commas, and then add in chromosome M, chromosome X, and chromosome Y. And then we close out the paste 0 here. And these are the rows. So remember how I said it's always rows and columns with R? So we're going in and we're saying, I only want the rows that have a chromosome name that matches one of these chromosome names. Okay, and that's what the in is doing. That's so handy. It's like find and replace or grab or grep, that is saying, in this column, find all the ones that match this and return those rows. And we left the columns blank here. So we left this sort of open, the comma empty. And that means keep all the columns. I still want all the information from the columns. So let's see what happens here. We run that. Okay, let's look at our data frame. And now we will see that GLO is gone. And we have chromosome X, Y, everybody's in there. And so that's great. We just got rid of all those weird parts of the genome that we don't quite want to look at yet, because nobody knows where they belong. Okay, so there's another way to do this is using the filter function. Go ahead and take a look at that. I like the tidyverse in aspect, but filter is another function where we can say, what is the data frame? So we don't have to index into it. And then it says, okay, what is the data frame? What is the column? And then we have the same in argument here in tidyverse. And that'll do the exact same thing. And if we want to get even more tidy with tidyverse, we can introduce the pipe here. So this is saying we're going to we're going to go into pull to peak one. We're going to take out only the rows that have normal chromosomes, and we're going to assign whatever happens over here to this new, rewrite it to that. And so what we see here is that we can say, here's the data frame. So now on this side of the operating arrow, the computer knows everything that's in that data frame in its memory. And so we're piping that memory to filter, and having filter say, okay, I know you have a column because I have it in my memory named chromosome, and tell me the one in that other tidy argument we used above. It's the exact same code. Okay, that's 3 different ways to do the same thing. This is often the case, and you can read more about the differences and these operators here. Just kind of going through it, pointing out the concepts, but all of it's written down so you can go back if we're going a little fast. Length is a very commonly used function in genomics data. So if we want to know the length of how many peaks there are, we can just do length is going to tell us the number of columns. And so that's saying defaulting to the data frame we have here, saying, okay, tell me the length of it, and it's 9 columns long. Now, if we look in here where we've now said, here's the data frame we want, index into the chromosome column with the cache sign there, then we get actually the number of rows or the length of that single column. And this will become second nature very soon. So it tells us there's about 33,493 peaks. That's pretty cool. So we can now know with just one quick command, index into the column and get the length of it. And we could do the same thing for a different column. Let's say we wanted to know the length of the name of peaks. Will give us the same answer there, same number of rows. Okay. Cool. So now we can use summary. So length is a great thing to look at, the length of a width or length of something. And then also summary gives us a bunch of statistical information. This is why I love R, is that it's really kind of based in statistics, and it can tell us that the summary of each column. So here we're looking at the minimum chromosome length is the number of peaks there are. And then the start has a minimum of starting at base 10,000 on a chromosome, a maximum of this. So it gives you the minimum, median, mean, maximum, and quartiles of every column in one little go here. So we could also then just index into start here. And again, it'll help you by autofilling to know that, okay, so we got just now one of the information for just one of the columns here, down here in the bottom left. Okay, cool. So yeah, summary is really powerful because it gives you not only the overall, but it can do it for all columns at once in your thing. Unless you want to, this same example here is with table. So if we do table this data frame, it's not going to be that useful. Let's see why. We run it, too many elements. It's like, now I can't deal with that. So we'll look at table by looking into a column first, and we'll look into Q value and table it. So table is the function in the parentheses. Pull to peak one is our data frame that we're indexing into the Q value column. And we can see this, ooh, that's kind of hard to read. But it says, like, for the Q value, that 1.3612 has one entry. Most of these will probably have just one entry because they're all very long numbers, and the odds of them having the same score would be low. Oh, there's one with 3. Okay, so 3 have a Q value of 1.0879. But this is not fun to read through. So you can do table. And basically what it's doing is saying, I know how many unique entries there are. I'm going to tell you how many times I saw that. And if we do now table this, it's going to tell us how many times there were 2, 3, or 4 values. And we can see that without having to scroll through it. So what we get here is that the vast majority only show up once. 711 have 2 entries. 27 have 3 entries, and 1 entry has 229. So that's good to know that when you're counting things up and want to know like how many overlaps there were, was there one overlap, two, three, that's where table will come in handy quite a bit. So that was table. So this is the opening bracket for that. RStudio will match it up for you. If you just click next to it, it'll tell you which one you're connected to. And so we see table, opened up into the data frame and column. We want a table, and then closed off on both sides. Okay, so let's learn a quick function here. Mutate is my favorite function. It basically makes a new column. It wants, its parameters are, tell me the column name that you want me to make, and then the function you want me to run on the data that put into that column. So if you wanted to add two columns, you could do mutate added column equals, and then add the two values. And so we'll do that here. We're gonna recommend using the manual. So in R, if you do question mark and the name of the function, you'll get the manual here, and it'll tell you the parameters to use. Whereas like, give me the data frame, which we'll use tidyverse pipe for. And then once it's in there, then it'll know all the column names, and you can then have it run a function here. Okay, so let's take a look at that, and we'll just do a real quick one and start analyzing our data. Get some first glimpse here. We already know there's 32,000 peaks. That's something. So what we're going to do is use our tidyverse, where we're going to rewrite over this object, but we're going to take that object and pipe it into the memory. So now anything to the right of this pipe will know everything about this data frame. We're going to call the mutate function with open parentheses, and we're going to make a new column called peak width, which equals, so this would be the mutate first parameter, peak width equals, and it knows that because it knows there's a column named end and start, so we don't have to index into them now. And that's the nice thing about this pipe. It's explained more here, but you can just have it in memory, so you can type the name of the column. We do have a start and end column here, so that will work. And so if we want to know the width of a given peak, because where does the peak start and where does the peak end, we can just subtract the two, and mutate will go through and do that for every row in your data set and do it in one quick swoop. So if we run that here and take a look at our data frame now, it usually puts it at the end, and we have a new column called peak width. That's so cool. So we just subtracted all of them and got a new column here. Mutate can run very complex functions. It can run functions inside of functions. We'll use mutate a lot, where we take some data and say, I want values of this times that and divide by this, etc., to normalize data and other ways. So it's a pretty simple function that taught us something. Like, what is the average width of the peaks? I don't know. Let's find out. So if we want to now look into that column we just made, we can use summary like we just saw, take this data frame and index into our new column peak width. And let's take a look. Okay, so we can see the minimum size of a peak is 114 nucleotides, so 114 letters of DNA, and the max rises in at 12,395 bases. So they can range from 100 to 12,000. The median size is 258 and the mean is 370. Meaning that on average, that's what they should, and that's what they should be, because the process actually involves shearing DNA to about 300 bases. So that's looking good. R has amazing plotting functions built into it, and ggplot, and we'll have a whole class on ggplot and how to use it. But for now, we can use some of the base R plotting programs, which is a histogram. So we can see like how we can look at this distribution across the whole spectrum. So let's run that. And again, it's an R function. So we open the parentheses here with hist. We have our pull to data frame. We're going into that column we just made, and we want to see what this looks like graphically. Okay, cool. So we see most of the peaks are under 2,000, and there's data all the way out here at 12,000. So let's set the scale a little better on this here. And so we can add in our hist function, here's our first parameter, what to plot. And then now we can do a comma and say breaks equals 50. So we're adding some more layers onto it. Another great thing with R and figures. So let's do that. And so if we have more breaks, we can see some of the data kind of decaying instead of just looking like one big brick before. And then we can add another thing, because most of the peaks seem to be before 4,000, or we can't really see them anymore. You can zoom in here and look closer, but it looks like somewhere around 3,000, our data is too small to see. So let's look in there, and we can add now our first parameters, data frame column, number of breaks, and then another comma to add another parameter and to make the X limits. Again, we're making this C to make a string of numbers, and so instead of characters this time. So it's from 0 to 3,000 is where it's going to say the limits of this plot should be. You run that, and we can really zoom in and see, okay, most of the peaks are really in this 250 to 300 range, and they kind of drop off at about 750. Okay, we're learning stuff. We're really starting to see this. We can see it the same way with the density plot. So a histogram is the frequency of it here, and we can look at this with density. You can look at the density manual and see what's going on. But basically, it's going to tell you where your data is, and we can look at this. And it's a very complicated thing, but it's basically saying in a given position how much of the data is there. And we can use plot to look at that object and just plot it. So we have our plot is our density object that we just created here with this assignment operator. Can't get my mouse to get big. There we go. The assignment operator that we just made by looking at the density of the peak width column. And now we're plotting it, opening up the parentheses to plot the density object, and the X limbs the same as we had before, separated with the comma. So what we can see here is that most of our data is here. So it's almost like a trend line on the histogram, but most of the data in that column is here, and we can see what fraction of it is. The area under this curve will equal 1. So 100% of your data, and we can see the largest portion of that fraction of that data is here. Okay, histogram density plots of peaks. This is great. We're analyzing data and we're getting values that look like they should. So we're going to do a lot more with ggplot, but here what we're going to do is just see how the p-value correlates with the size of the peak. So is a bigger peak going to be more significant in the statistics? We can take a look at that, where we're saying to ggplot, take our data frame, pipe it in there so you know everything about it already, setting the X and Y value to the column peak width and the Y to the Q value. Again, we're going to do so much more with ggplot. This is just so you can kind of see a little more analysis here, and that we don't really see a linear. We'd expect if the peak width got bigger, they'd be more significant. They'd be up here. You know, that's that. But what we've seen here is how to read in a file. What are the columns? How to rename the columns? How to add names to them? How to make a new column with mutate, a histogram, and a density plot. And I think that's a great start. Our data is looking good, and I have an exercise here for you to look at using mutate, make a few more columns in your data frame and analyze the data. Okay, and then we're going to take it some more steps, do some find overlaps, and keep pushing along on the analysis using and learning R at the same time. So the goal is to learn R and apply it to things with our data that we just generated, and get deeper and deeper into the genome binding of DNA binding proteins. All right, thank you very much, and be well.